All right, welcome. Today, we are diving deep into a concept that is, quite literally, the backbone of almost every single app and website you use. It's called Object-Oriented Programming, or OOP for short. It's a way of thinking about code that took software development from total chaos to crystal clarity. Let's get into it. Really think about it for a second. Your phone, your laptop, the games you play, they're all juggling millions of different things at once. How on earth does all that complexity not just, collapse on itself? The secret is a really brilliant way of organizing things. In the early days of programming, things were kind of like this, just a chaotic jumble of ideas and commands. And as programs got bigger and more complicated, it was like trying to build an entire city with zero blueprints. Every single piece was custom-made, which led to code that was messy, a nightmare to manage, and basically impossible to scale up.
And that really gets to the heart of the problem that these older programming styles faced. As projects went from being a tiny little shack to a massive skyscraper, that lack of structure became a huge project-killing issue.
This really shows the massive shift in thinking. The old way was basically one long, rigid scroll of instructions, top to bottom. But OOP, it introduced a totally new way of thinking, building with reusable components. Think of it like going from custom carving every single stone to using standardized bricks. Suddenly, your code is organized and you can build bigger, better things way faster.
So, how does this all work? Well, OOP is all about thinking in terms of objects, which is actually how we humans see the world, right? And to do that, you need a way to design these digital objects first. You need a master blueprint. And in the world of OOP, that blueprint is called a class. Now, it's super important to get this. A class isn't the thing itself. It's not the car. It's the detailed design document for the car. It says every car will have 4 wheels, an engine, and it will have the ability to accelerate and brake. It's the pure concept. And from that class, from that blueprint, we create an object. The object is the actual car that rolls off the assembly line. It's a real, tangible thing made from the blueprint. You can have thousands of car objects, each with its own unique color or mileage, but every single one of them started from that one car class.
Now, this whole blueprint and object system is held up by 4 incredibly powerful ideas. And these aren't just a boring list of rules, they're more like the essential tools that a master builder uses to create software that's tough, flexible, and super efficient.
So, let's start with the first one, inheritance. This pillar is all about being efficient. Why would you design a brand new sports car from total scratch when you could just start with the general vehicle blueprint that already has things like wheels and an engine figured out? Inheritance lets you do exactly that. Okay, so let's see what this looks like. The diagram shows a superclass, Class A, which has some basic stuff defined. Now, instead of rebuilding all that from scratch, Class B, which is a subclass, can just, inherit it. Imagine Class A is a person with a name and an age. A more specific class, like student, could just inherit those traits and then add the new stuff, like a student ID number. It's all about reusability. It's a game changer. All right, next up we've got encapsulation. This pillar is all about safety and simplicity. It's the idea of bundling an object's data and the methods that are allowed to change that data all together into one neat, self-contained little package.
This little piece of code shows it perfectly. See how the student class bundles its data, like name and age, together with the methods that can interact with it? And notice how the variables are marked private? That creates a kind of protective bubble. You can't just reach in from the outside and change a student's age directly. Nope, you have to use the public get or set methods. This is huge because it prevents accidental mistakes and keeps the object's internal workings safe and secure.
And that idea of a protective bubble leads us right to our third pillar, abstraction. As the quote says, it's all about hiding the messy internal details and only showing the stuff you actually need to use. Think about the send message button on your phone. You just press it, right? You don't see all the crazy complex stuff happening behind the scenes, the data encoding, connecting to a cell tower, all that network routing. All of that complexity is abstracted away, leaving you with a simple, clean button to press. That is the core idea of abstraction.
And our final pillar is polymorphism. Now, that's a big word that literally just means many forms, and it's an incredibly powerful idea. It means the same action can behave differently depending on the object it's acting on. So, for example, you could have a program with dog, cat, and duck objects. If you tell each one to perform the same action, make sound, well, the dog object barks,
The cat meows and the duck quacks. It's one single command, but it produces many different results. This makes your code unbelievably flexible.
So there we have it: inheritance, encapsulation, abstraction, and polymorphism. These 4 pillars work together to let us build a better digital world. But what's the actual real-world payoff? Why go to all this trouble to organize our code this way?
Well, the payoff is huge. Inheritance gives us that amazing code reusability we talked about, which saves just countless hours of work. Encapsulation gives us robust data hiding, which makes our programs way more secure and reliable. The whole organized structure makes maintenance, fixing bugs and adding new features, so much easier. And when you put it all together, it lets us model really complex real-world systems inside a computer with amazing accuracy. So, in the end, OOP was a genuine revolution. It took programming from being this tangled, linear mess of instructions and turned it into a clear, intuitive way of building with, digital Legos. It taught our computers to see the world less like a giant wall of text and more like a collection of distinct things, each with its own purpose, which is pretty much exactly how we see the world, too.
And that leaves us with a really fascinating thought, doesn't it? This method of using blueprints, creating these self-contained units, and managing complexity totally revolutionized software. So what other complex systems in our lives, maybe in how we run a business or in education, or even in our own personal projects, what else could benefit from thinking in objects?